Hello and thanks for joining me in the studio today as we talk about control signals used in synthesizers. On the screen there you're viewing the envelope generator from the synthesizers.com rig. This is the standard envelope generator, the Q109. Now as you can see, we have it triggering from a slow square wave, and observe that we have some attack time there. The attack time is set to about nearly 2. We have no decay time. We have the sustain time set to about halfway, and we have no release time. And observe the cycle there in the triggering of the envelope generator. Now on the oscilloscope, what we're seeing is consistent with what we have. Notice that we have the complete fall off there after the sustain period down to 0, and we have a curve coming from 0 up to the maximum with absolutely no decay, dropping back down to the sustain level. The Q109 is not going to have straight lines for the attack and the decay and the release times, because it depends upon the charging and the discharging of the capacitors. So I'm going to now change it a little bit. I'm going to put some decay time, some release time, and maybe a little longer attack time. Let's change it here on the unit. Let's increase the attack time a little bit. Let's put some decay time, and let's come and let's put some release time, and let's see what we have on the oscilloscope. Now this is really an example where the digital oscilloscope shines through, because for these kind of slow times you wouldn't be able to get such a nice steady waveform on the analog oscilloscope because of the necessity of having the phosphor tracing. But because this LCD is drawn from memory, we have a much better chance of seeing a perfect waveform on our digital oscilloscope. So notice that we have a longer attack time coming up there to the maximum of about 5 volts, and then we have a little decay, a gradual decay down to the release time. And then at that point there you can see where the release starts after the sustain level. So we can see quite clearly in this oscilloscope wave, we can see the attack period, the decay period, and the sustain level and the release time. So let's raise the sustain, shorten the decay, and see what happens. We're going to raise the sustain level a little bit more. We are going to shorten the decay, and we said we would shorten the release. Well, as you would expect, the flat part, which is right to the point of key off when the thing terminates there with the release period at the very end, now that is our classic ADSR behavior of our envelope generator. Now what the possibilities are with the control signals is almost endless, because we can use our slope module, we can use a number of other advanced envelope generators, the EG++, or we can even make more fancy controls by mixing oscillator waveforms. And we were hoping to demonstrate that in the video this afternoon. We've transferred it to the Slew limiter. Let's turn up the amount on the Slew limiter fairly high. Now notice we have it set to both. So we're getting a slew both on the rising and falling edge of our control signal, as you can see there. Now we leave that and we'll just, the beauty of the slew limiter is that it allows us to have it on one edge or both. So that's in both directions. That's in the down direction now. Watch and see what happens next. Right, we only get the slewing on the falling edge. And now we're only going to get the slew. We're going to transfer the slew now to the rising edge. There we go. So it's beautiful to be able to say these time varying changes in the control signal. And as I said, you need to buy a digital oscilloscope to be able to observe them, because they typically take place over a much longer period of time since they're sub-audio. Okay, we're now looking at the ADSR for the envelope plus, and as you see, this one actually has straight linear lines for the time period. As you can see with the envelope plus, we have a curve switch here, and this we just toggle it up. The middle position gives us several different curves, so we can actually toggle 4 or 5 different curves, and the LED shows us at the bottom what part of the cycle it's in. So let's move it down to the middle now and see what we get. Now, as you can see here, the curve is moving a little upwards of the linear position, so we're getting a sort of bow in the upward direction from the straight line linear. I want to make sure that you see that. I think this is the one they call bumpy in the literature. Alright, this one's the one they call exponential. As you can see, it's curving in the other direction for the most part. Okay guys, this is definitely the one that they call peaky in the literature. And finally, this is the one that's logarithmic. With this envelope, as you can see, we can also have a hold time. Now when we have the hold time after the attack and before the decay, because we only have 4 knobs, we can adjust the hold time, but that means that the decay and the release rate will be the same. The same knob affects the two of them together. That's the bumpy with the hold time. That's the exponential with the hold time. That's the peaky with the hold time. And that's the logarithmic with the hold time. We can produce a stepped control voltage as shown here to cycle through pitches or do whatever we want with it. We come now to sample and hold, which is a great way of getting a random control voltage. As you can see there, I have a square wave, and every time the square wave goes through a cycle, we take a sample of a random noise source so that the level changes, and this is a truly random voltage, and we can make it more random by increasing the noise bandwidth. Now the thing about it is, when you look at this, you see steps, and these steps can translate to random pitches, as you have seen, but it could also be used for other things. You could trigger filters, you could trigger VCAs. So a control voltage can be used to control anything. However, what I'm interested in telling you right now is that we can actually round off some of these steps with using our slew limiter. We can actually turn that into a slowly varying voltage instead of a jumping step like what you've seen there. But clearly you see that our control voltages are divided into either a cyclical thing, which is like what we're using with our envelope generator, a random thing like what we have here, or perhaps a single trigger that goes through a particular cycle. So if we have a single trigger, that would correlate to some kind of timbre change on a note. If we have a continuous cyclical thing or a random thing that continues over time, that can be used as a modulation. So thanks for watching the Stephen Mendes channel, and we'll hope to see you in the next video.